Welcome to the Deep Dive, where we cut through the noise to get you truly well-informed. Now, if you've ever worked in IT, or, well, even just dealt with an IT issue, you probably know the feeling.
Oh, yeah.
It's like being a firefighter,
Yeah.
constantly rushing around, putting out these blazes.
Always reactive.
Exactly. A report server hangs. Maybe a critical database query just grinds to a halt. Or customer-facing services start to degrade. And suddenly, bang, you've breached those crucial service-level agreements.
Those SLAs, yeah. The promises you made.
Right. And it's stressful, it's incredibly inefficient, and honestly, it just hits the business right in the wallet. This whole reactive model, it just feels like a perpetual emergency, always putting out fires after they've already started.
It's exhausting for the teams involved.
Totally. But what if you could actually predict those fires?
Yeah.
Before they even sparked?
Now that's the interesting part.
That's exactly what we're diving into today. AIOps, artificial intelligence for IT operations. And look, this isn't just another buzzword you'll hear flying around.
No, it's becoming really fundamental.
It is. It's rapidly becoming the definitive modern solution. A true paradigm shift, really. It's about moving from constantly reacting to, well, actively predicting and preventing incidents.
That's the core idea.
So our mission for you today is pretty clear. We're going to unpack how AIOps uses things like big data, machine learning, and automation to completely transform IT.
Right.
We're moving from just reducing mean time to resolution, MTTR, which is just fixing things faster after they break.
Which is good, but not ideal.
To something way more powerful, predictive incident avoidance.
Yeah.
Actually stopping them before they happen.
Yes, and that shift, that move to predictive avoidance, that's precisely what we'll explore. We're going to give you a really comprehensive understanding of this whole transformation.
Right.
We'll cover, the strategic why, dive into the technical architecture, the how, and even look at the specific AI model that actually make it all work.
Excellent. So you'll get the full picture.
Exactly.
Okay, let's unpack the core problem here. The one AIOps is designed to solve. Modern IT environments are just mind-bogglingly complex now.
Unbelievably so.
We're talking cloud-native stuff, microservices, hybrid setups, and it all generates this tsunami of data.
Yeah, logs, metrics, traces,
Yeah.
events. It's overwhelming.
It is. It's way beyond what any human team can possibly oversee manually. And it's this explosion, right? The data, the complexity, that's what traps teams in that constant firefighting mode we talked about.
What's really fascinating, I think, is how AIOps just emerges as this direct sort of intelligent response to that escalating complexity. Gartner, the research firm, they actually coined the term back in 2016, and they defined it basically as applying big data and machine learning to automate and genuinely enhance IT operations.
But taking that flood of data and making sense of it.
Exactly, at a scale humans just can't match.
Right. So the fundamental shift here is, it's pretty dramatic, isn't it?
It really is.
Traditional monitoring, it's inherently reactive. It tells you after something's broken, right? After a threshold's been breached.
Yeah, the damage is already starting.
But AIOps is designed to be predictive. It's about spotting those subtle patterns, those tiny deviations in real-time data before things actually go wrong.
Finding the signals in the noise.
Yeah, it forecasts and prevents. It's kind of like moving from a fire department that only rushes to burning buildings to one that can actually spot faulty wiring beforehand and stop the fire from ever starting.
That's a great analogy.
So, okay, what does this actually mean for the business? The bottom line. Well, AIOps delivers value across, I'd say, 3 really critical areas.
Okay.
First, there's the direct financial impact. Think about it. By spotting those early warning signs like performance starting to degrade or some weird resource usage.
Things humans might miss.
Exactly. AIOps lets teams jump in before a full-blown outage hits. And that's not just about fixing things faster. It's about actually preventing lost revenue, avoiding those expensive SLA penalties.
And keeping customers happy. Trust is huge.
Absolutely. Plus, it directly lowers operational costs, automating routine stuff, optimizing resource use so you're not overspending.
And maybe consolidating some of those pricey legacy monitoring tools.
Right. So that's the money side. Then number 2, you've got the operational efficiency gains.
This is a big one for the teams themselves.
Huge. AIOps dramatically speeds up root cause analysis RCA. Instead of engineers digging through logs for hours.
Which is painful.
AIOps uses algorithms to correlate massive amounts of data metrics, logs, traces, event data, change data, all in real time. It can pinpoint the actual root cause in minutes, sometimes seconds.
That's a massive time saver.
And for anyone who suffered from alert fatigue, getting hundreds of alerts for what's really just one underlying issue.
Oh, everyone in ops knows that feeling.
AIOps is a lifesaver there. It intelligently groups related alerts into like a single actionable incident. It cuts through the noise and tells you what really matters.
So you focus on the real problem.
Exactly. And finally, number 3, strategic business enablement. This kind of raises an important question, doesn't it? What happens when your best tech people aren't constantly putting out fires?
They can actually build things, innovate.
Precisely. AIOps frees up your most valuable folks, your DevOps engineers, your site reliability engineers, SREs from that endless reactive grind.
The toil, as they call it.
Right. And that lets them focus on strategic stuff. Building more resilient systems in the first place, developing cool new features for customers, improving the whole software pipeline.
It creates this kind of positive feedback loop, right?
Yeah, a virtuous cycle. Better systems mean fewer incidents, which frees up more time for innovation, which leads to even better systems. It directly speeds up your innovation velocity.
That's a crucial point. And, to actually deliver all this value, AIOps really relies on 3 foundational capabilities, or you could call them key use cases.
Okay, what are they?
First is anomaly detection, automatically spotting when things deviate from normal. Second, event correlation, connecting the dots between maybe thousands of separate alerts to see the bigger picture, the actual incident. And third, predictive analytics, using forecasting to anticipate what might happen next in the system.
Got it. Anomaly detection, event correlation, predictive analytics.
Exactly. And it's really important to understand implementing AIOps isn't just, buying some new software. It's a whole strategy. It genuinely requires a cultural shift and collaboration across different teams, ops, DevOps, SREs, to really work well.
Right. It's not just a tool, it's a way of working.
Precisely.
Okay, so we've covered the what and the why of AIOps. Pretty compelling. Now let's dig into the how. How does this stuff actually work under the hood?
Right.
You said it's not some monolithic black box. You described it more like a sophisticated data pipeline.
Exactly. Think of it as a data-centric pipeline, a series of connected layers designed to turn raw, noisy data into intelligent, automated action. You can basically picture it as a 4-stage process flowing sequentially. Stage 1 is data ingestion and integration. This is what we often call the observe phase.
Observe. Makes sense.
And it's absolutely foundational because its main job is breaking down those data silos we all struggle with.
Everywhere, yeah.
It needs to pull in diverse data from, everywhere in your stack. On-prem, cloud, hybrid. That includes the core observability data, metrics, logs, traces.
Technical stuff.
Right. But critically, it also needs to ingest what we call interaction data. Things like incident tickets from your ITSM system, like ServiceNow, maybe.
Yeah, common one.
And change records from your CI/CD pipelines. This adds vital human and process context. What changed, who's working on what.
Okay. So not just machine data.
No, that context is key.
Yeah.
And this layer uses things like high-performance stream processing and needs to integrate with hundreds of different tools. Prometheus, ServiceNow, AWS CloudWatch, you name it.
Gotcha. So that's stage 1. Observe, ingest everything. What's next?
Stage 2 is the centralized data platform. This is the aggregate phase. Think of this as the single source of truth for all that ingested data.
Okay, the central hub.
Exactly. It has to be a big data architecture, really, designed specifically for the crazy volume, velocity, and variety of IT operations data.
Needs serious horsepower.
Absolutely. We're talking about architectures like data lake houses, maybe, which try to blend the scalability of data lakes with the performance and structure of data warehouses. This layer handles storing the data, obviously, but also does crucial prep work. Data curation, cleaning it up, normalizing different formats, transforming it so it's ready for analysis, getting rid of the noise.
Preparing it for the smart stuff.
Right. Which brings us to stage 3, the intelligence layer. This is the analyze phase. This is really the brain of the whole AIOps platform.
Where the AI happens.
Precisely. Here, various machine learning models, advanced analytics engines, they get applied to that clean, curated data from the platform. This is where the patterns get uncovered, the anomalies are flagged, the predictions are generated. It turns data into actionable intelligence.
Cool. So observe, aggregate, analyze. What's the last step?
The final stage is the automation and action layer, the act phase. Because, I mean, intelligence is useless if you don't act on it, right?
It's true. No operational value.
Exactly. So this layer translates those insights, those predictions into concrete automated responses. Now, the actions can be on a spectrum.
Okay.
It could be intelligent alerts, context-rich notifications sent to the right team via Slack or PagerDuty, or it could be automatically creating and routing incident tickets in ServiceNow.
Automating the workflow.
Right. But the ultimate goal, the sort of holy grail, is self-healing workflows, where the AIOps platform itself can automatically trigger actions like restarting a failed service or scaling up cloud resources without any human needing to intervene.
Wow, okay. Closing the loop automatically.
That's the aim. Observe, aggregate, analyze, act. That's the pipeline.
We've talked about collecting all this data. Metrics, logs, tickets. But it still feels like it could just be noise without context, right?
Absolutely. Context is everything.
How does AIOps actually make sense of it? How does it know what's really critical versus just background chatter?
Okay. That's where something called topology becomes absolutely foundational.
Topology. Okay, what is that exactly?
Think of topology as the dynamic real-time map of all your IT assets, your applications, your services, the processes running, the hosts, containers, network devices, everything.
Like a blueprint of the system.
Kind of, but crucially, it also maps their intricate interdependencies, how everything is connected and relies on everything else.
Okay. The relationships.
Yes. Without that clear understanding of dependencies, all the data you ingest is just, well, it's a collection of disconnected signals.
Give me an example.
Okay, sure. Let's say you see a CPU spike on a particular server on its own. Could be anything, maybe just noise. But if the topology map shows that this specific server hosts the database for 5 critical customer-facing applications.
Then that CPU spike is suddenly a big deal.
Exactly.
Well,
It's instantly contextualized as a high-priority event with potentially massive business impact. Topology is absolutely key for doing accurate root cause analysis, too. It lets the system trace how a failure might cascade through that dependency chain.
I see. So you can follow the problem.
Precisely. And the leading AIOps platforms are designed to automatically discover these complex relationships and keep that map constantly updated in real time, because environments change constantly.
That makes a lot of sense. Topology sounds critical.
It is. And building on that point, it really underscores the importance of having the right essential data sources. To build a truly predictive system, you need a comprehensive data strategy, not just metrics.
Right. You mentioned tickets and changes earlier.
Yeah. We can broadly categorize the needed data. First, observability data, that's your metrics, logs, traces, gives you the real-time performance view.
What's happening now?
Then, interaction and engagement data, like those ITSM tickets, change management records. This provides crucial context about how humans and processes are interacting with the systems, who did what, when.
The why and who.
Kind of. And finally, contextual and qualitative data. This includes topology, which we just discussed, but also things like human or tribal knowledge, operator notes, run books, observations.
Plain enough, it's often stuck in people's head.
Exactly. And also asset and maintenance data. Now, what's really crucial here is that quality and context are actually far more critical than just having sheer quantity of data.
So more data isn't always better.
Not necessarily. The real power, the predictive magic, is unlocked not by looking at one data type in isolation, but by intelligently correlating data across all these different categories, connecting the dots between a performance dip, a recent code change, and an open incident ticket, for example.
Got it. Correlation across sources is key. Okay, this is fascinating. Now, let's dive into the brain itself. You called it the intelligence layer. Let's talk about the specific AI models that actually do the work, that transform all that correlated data into predictions. This is where the magic happens, right?
Indeed it is. This is where the algorithms chew on the data. First up, a foundational one. Anomaly detection.
Finding the weird stuff.
Exactly. It's fundamental for moving from reactive to proactive. It helps identify those unknown unknowns, those subtle, unexpected deviations from normal behavior that are often the very earliest signs of trouble brewing.
Okay.
And this really marks a shift away from those old, brittle, static thresholds. Alert me when CPU hits 90%.
Yeah, which often trigger too late or create noise.
Right. Instead, AIOps uses dynamic baselining. Machine learning models actually learn what normal behavior looks like for each specific system, including its unique daily or weekly cycles.
So it understands the system's rhythm.
Precisely. And then it only alerts when there's a statistically significant deviation from that specific system's learned norm. Much smarter.
What kind of algorithms do that?
Well, there's a range. For simple single variable data, like maybe network latency on one link, basic statistical methods like z-score or interquartile range can work quite well.
Okay.
But for more complex, high-dimensional data, like analyzing hundreds of metrics from a server at once, where you don't have pre-labeled examples of good versus bad.
Which is common, right? You don't always know what failure looks like in advance.
Exactly. That's where unsupervised machine learning methods are vital. Think algorithms like isolation forests, k-means clustering, or Gaussian distribution models. These are clever enough to find unusual patterns or outliers in data, even when they haven't been explicitly trained on what bad looks like. Perfect for spotting novel issues.
Finding things you weren't expecting.
Right. And for really complex data types, like distributed traces that show how requests flow through microservices, deep learning models like autoencoders are sometimes used.
Okay. Now, what about logs? You mentioned logs are mostly text. How does AI handle that?
Great question. This is where the power of natural language processing, or NLP, comes into play, specifically for log anomaly detection. A massive amount of operational insight is buried in unstructured log messages.
Terabytes of text.
Exactly. So NLP helps first by doing things like log categorization or clustering grouping similar log messages together. Then the system can detect anomalies like a sudden spike in a rare error category that normally never appears.
Okay, finding unusual message types.
Yes. But it gets even more sophisticated. More advanced NLP techniques, especially those found in large language models, LLMs like the transformer architecture that powers things like ChatGPT.
The same tech?
Yeah, the same underlying principles. These models can actually understand the semantic context of log messages. They can grasp the meaning.
So not just keywords.
Right. It means they can tell the difference between, say, a log message saying connection closed, probably benign, and one saying connection refused, likely critical, even though they share words. This deeper understanding leads to much higher accuracy in spotting real problems within logs.
That's incredibly powerful. Okay, so anomaly detection finds the unknown unknowns, the unexpected deviations. But what about the stuff we know will eventually cause problems if we don't watch it? Like running out of disk space or memory.
Right, the known unknowns, in a way. That's precisely where time series forecasting comes in.
Predicting the future based on the past.
Exactly. This capability directly tackles resource exhaustion. It predicts future values of key metrics, CPU, memory usage, disk space, network bandwidth, based on their historical patterns and trends.
So you get a heads up.
Yes. The goal is to get proactive alerts like, warning, disk partition data is projected to be full in 48 hours, or alert, application server memory usage is forecast to reach critical levels around 2:00 p.m. today.
Giving teams time to actually do something before the crash.
Precisely. Prevent the outage altogether.
What kinds of models are used for that? Is it different from anomaly detection?
It often is, yes. For time series with clear trends and seasonality, like, say, daily web traffic patterns, classical statistical models like ARIMA, autoregressive integrated moving average, can be quite effective.
Okay.
For simpler, highly predictable linear trends, maybe like a disk filling up at a steady rate, basic linear prediction might be enough.
Simple, but does the job.
Sometimes. But for more complex nonlinear patterns, which are very common in modern dynamic systems, think fluctuating application traffic, you generally need more sophisticated advanced neural networks.
Like what?
Models like LSTMs, long short-term memory networks, are really good at capturing long-term dependencies in sequential data, making them great for predicting dynamic workloads.
Okay.
And interestingly, getting back to those transformers, the architecture behind LLMs, they're also proving incredibly powerful for time series forecasting. There are models now, like Amazon's Chronos, for example, that use transformer principles to achieve remarkable zero-shot forecasting.
Zero shot? What's that mean?
It means they can often make surprisingly accurate predictions on new time series data they've never seen before, without needing to be specifically trained on that particular data stream first. It's a very exciting development.
Wow. So the same core tech is useful for understanding language and predicting future resource usage.
It seems so. The ability to model complex sequences and dependencies is key in both cases.
Okay, so we can detect anomalies, we can forecast resource issues. Once an issue is detected or predicted, how do we make sure the right people get notified quickly? And how do we prioritize? How does AIOps automate that crucial triage step?
Ah, yes, triage. That's the domain of incident classification and severity prediction.
Making sure the right alarm bells ring for the right problem.
Exactly. These models aim to automatically predict an incoming incidents category, like database issue or network problem, its likely priority or severity, and maybe even its potential business impact, all based on the initial signals, the alerts, the logs, the topology context.
So it routes the problem automatically.
Ideally, yes. Or at least provides that classification instantly to the human responders, ensuring the right experts get engaged immediately without manual sorting.
What models work well here?
Well, for classification tasks using structured data like metrics, alert counts, topology info-cabined, traditional machine learning classifiers are very common and effective. Think models like random forest or gradient boosting machines like XGBoost and LightGBM.
Okay.
They tend to be highly accurate and often quite interpretable, meaning you can understand why the model made a certain classification.
But what about all that text data again? Error messages, user ticket descriptions.
Great point. That brings us back to the transformative role of large language models, LLMs. A huge challenge has always been how to effectively use the rich information buried in unstructured text for classification.
Yeah, how do you feed an error message into XGBoost?
Traditionally, it involved complex manual feature engineering trying to extract keywords or patterns. But LLMs, like BERT for instance, offer a much better way. They can convert that raw text into what are called rich embeddings.
Embedding.
Yeah, they're essentially dense numerical vectors, like coordinates in a high-dimensional space, that capture the deep semantic meaning of the text. Words and phrases with similar meanings end up close together in this space.
So the model understands the meaning, not just the words.
Exactly. And when you take these high-quality text embeddings and use them as input features alongside your traditional structured data, metrics, topology, etc., and then feed all of that into a classifier like XGBoost.
You get much better predictions.
Dramatically better prediction accuracy, often. And it hugely simplifies that painful feature engineering process. It lets the LLM handle the complexity of understanding the text.
That's a powerful combination, LLMs for text understanding, traditional classifiers for the structured data.
It really is. It leverages the strengths of both. But, it's really important to emphasize again, there's no single best AI model that solves all operational problems.
Right, no silver bullet.
No. A mature, effective AIOps strategy really requires a portfolio of different models, anomaly detectors, forecasters, classifiers, maybe others, each chosen and tuned for the specific use case and data type it's best suited for.
Makes sense. Use the right tool for the job.
Exactly.
Now, I find this fascinating. The journey doesn't just stop once you deploy these models, right?
Oh, absolutely not.
Because IT environments are constantly changing. New code gets deployed, infrastructure gets updated, user behavior shifts. That's just constant, isn't it?
It's the only constant, really. And you've hit on a truly critical challenge in AIOps. Concept drift.
Concept drift. Okay, what's that?
Basically, it means the statistical properties of the data your models were trained on start to change over time because the underlying system itself is changing.
So the model learned isn't normal anymore.
Precisely. A model trained on data from 6 months ago or even 6 weeks ago might perform really poorly on today's data. Its predictions become inaccurate, its anomaly detection flags the wrong things. It basically becomes useless or worse, misleading.
Okay, that sounds like a major problem. How do you deal with that?
You deal with it by embracing MLOps principles, machine learning operations.
MLOps. Like DevOps, but for machine learning.
Very much so. It's a set of practices that combines ML, data engineering, and DevOps. In the context of AIOps, it absolutely must include continuous monitoring of how well the AI models are actually performing in production.
Watching the watchers.
Kind of, yeah. And crucially, it requires automated retraining of models. This might be on a regular schedule or triggered automatically when monitoring detects that a model's performance has started to degrade due to drift.
So the models keep learning and adapting.
They have to. An AIOps platform that treats its models as static, kind of deploy and forget artifacts, well, it's simply not suited for the dynamic reality of modern IT operations. Continuous learning and adaptation are essential.
That's a really important point. The system has to evolve with the environment.
Couldn't agree more.
So, okay, wrapping this up. We've really gone from that stressful, reactive firefighting mode that so many IT teams live in,
day out,
to a genuinely proactive predictive state, all thanks to AIOps. We've seen how it can directly save money, massively boost operational efficiency, and maybe most importantly, free up those highly skilled engineers to actually innovate. It really does feel like a paradigm shift.
It absolutely is. And, if we connect this to the bigger picture, AIOps isn't just about deploying some new tools or
Right, you
algorithms.
said it's cultural too.
It is. It's about a fundamental shift in how organizations perceive and manage their entire digital infrastructure. It has the potential to turn IT operations from being seen primarily as a cost center into a truly strategic asset that drives business value.
Making IT a proactive partner in the business.
That's the goal.
All right, and for you, our listener, here's a final provocative thought to mull over. Considering the incredible speed at which technology is evolving and how AI ops relies on these predictive capabilities and models that need constant learning, how might this integration fundamentally reshape the future job roles and the actual skill sets needed for IT professionals down the road?
Good question.
Think about the implications. What does it mean for your own role, maybe, or for your organization? Something to definitely think about.